You're welcome back to class. Today we want to study atoms and elements. That is, we are on chapter 2. So we'll look at some of the theories, the atomic theories, modern atomic theory and law. So we have the law of conservation of mass. And in this law, it states that in a chemical reaction, matter is neither created nor destroyed. It means the total mass of material you have before a reaction must equal the total mass of the material that you have at the end of your reaction. That is, total mass of reactant must be equal to total mass of product. This is the law of conservation of mass. We are going to look at another law. The law of definite proportion. And this law states that all samples of a given compound, regardless of their source or how they were prepared, have the same proportion of their constituent elements. Have the same proportion of their constituent element. That is a law of definite proportion. So we are going to examine the law in sodium chloride. If we have 100 grams of sodium chloride, we expect it to contain 39.3 grams of sodium and 60.7 grams of chlorine. So let's look at the proportion of chlorine to that of sodium in this 100 grams of sodium chloride. So we are going to put chlorine up and the mass of sodium down. You'll notice that in 100 grams sample of sodium chloride, the ratio of chlorine and sodium is 1.54. Now let's take 200 grams of sodium chloride. We are trying to validate this law of definite proportion. We are taking different masses of sodium chloride. So this time we have 200 grams sample of sodium chloride. And in 200 grams of sample of sodium chloride, we have 78 grams of sodium and 121.4 grams of chlorine. Now let's get the ratio. So the mass of chlorine over the mass of sodium, when you do this math, it gives us the same ratio as we had for 100 grams of sodium chloride, 1.54. Now we want to reduce the mass. Now we want 58.44 grams of sodium chloride. And in 58.44 grams of sodium chloride, we have 22.99 grams of sodium and 35.44 grams of chlorine. Let's find the ratio of chlorine to that of sodium in this sample also. So you notice that in this sample, we still come up with 1.54 as the ratio. So this validates the fact that the proportion of the elements is definite, irrespective of the source and the mass of the substance. Let's take another example. So this example, let's look at it. We are trying to validate the law of definite proportion. The question shows that it reads that, show that two samples of carbon dioxide obey the law of definite proportion. So we have sample 1, and in sample 1, we have 25.6 grams of oxygen and 9.6 grams of carbon. Now we are going to find the ratio of oxygen and carbon in sample 1. So when the ratio, the proportion of oxygen and carbon in sample 1, it is 2.67. That is for sample 1. Now let's look at sample 2. In sample 2, we have 21.6 grams of oxygen and 8.1 gram of carbon. Let's see what the proportion of the elements will be. So this is sample 2. The ratio of oxygen and carbon is also 2.67. So it shows that carbon dioxide obeys the law of definite proportion. So since both samples have the same ratio of oxygen and carbon, the result is consistent with the law of definite proportion. We want to look at another law, the law of multiple proportion. I hope you are with me. Let's look at another law, the law of multiple proportion. The law of multiple proportion states that when two elements, A and B, form two different compounds, the masses of B that combines with 1 gram of A can be expressed as a ratio of small whole numbers. I'll go again so that we understand it. It says, when two elements, A and B, form different compounds, they have to form different compounds. For example, we have calcium chloride, or we have calcium chloride. You see, this has 2 chlorine atoms. This one has 1 chlorine atom. This is just an example. I'm not saying that it's an element. This is just an example. I just want you to look at what we are saying, A and B. So calcium and chlorine, calcium and chlorine. So let's continue. We want to look at this law with respect to carbon monoxide and carbon dioxide. So carbon combines with oxygen to form 2 different compounds, carbon monoxide and carbon dioxide. We are investigating the law of multiple proportion. So carbon monoxide contains 1.3 grams of oxygen for every 1 gram of carbon. But carbon dioxide contains 2.67 grams of oxygen for every 1 gram of carbon. So since there are twice as many oxygen atoms per carbon atom in carbon dioxide than in carbon monoxide, the oxygen mass ratio should be 2. So that is what the law of multiple proportion is about. So mass of oxygen that combines with 1 gram of carbon in carbon dioxide over mass of oxygen that combines with 1 gram of carbon in carbon monoxide is 2. small whole number ratios. Let's try this example. Hematite contains 2.327 grams of iron for every 1 gram of oxygen. Litharge contains 3.490 grams of iron for every 1 gram of oxygen. Show these results are consistent with the law of multiple proportion. So that's what we want to show. And how do you do this? So this is the mass of iron in hematite that combines with 1 gram of oxygen. In litharge, we have 3.49 grams of iron combining with 1 gram of oxygen. So mass of litharge per 1 gram of oxygen over mass of iron in litharge per 1 gram of oxygen over mass of iron in hematite per 1 gram of oxygen, it gave us 1.5. Because we want small whole number ratios, we are going to multiply this by 2. So this will become 2. This will become, so this ratio, this is a ratio. So it's just showing that we have this over 1. So multiply all this by 2. We are going to have 3:2. That's what we are going to have. Because we want whole numbers. So let's get this. So that's what you see, 3:2. That's how they got it. So we have looked at the law of mass conservation. We have looked at the law of definite proportion. We have looked at the law of multiple proportion. Now we want to talk about Dalton's atomic theory. Dalton's atomic theory was proposed in 1808 by Dalton. And the theory explains the law of definite proportion and the law of multiple proportion. So, according to Dalton, each element is composed of a tiny, indestructible particle called atoms. Point number 2, Dalton says all atoms of a given element have the same mass and other properties that distinguish them from atoms of other elements. He also proposed the third proposal that he gave is that atoms combine in simple whole number ratios to form compounds. And his fourth proposal is that in a chemical reaction, atoms of one element cannot change into atoms of another element. That's his proposal. So these are the proposals that Dalton proposed in his theory. Proposal number 1, each element is composed of tiny indestructible particles called atoms. Proposal number 2, all atoms of a given element have the same mass and other properties that distinguish them from atoms of other elements. And proposal number 3, atoms combine in simple whole number ratios to form compounds. Then proposal number 4, so in a chemical reaction, atoms of one element cannot change into atoms of another element. So that was Dalton's proposal, or Dalton's atomic theory. So after scientists have discovered that matter is made up of atoms, now they started investigating atoms. And let's see what they discovered. By late 19th century, scientists were convinced that matter was made from atoms. With that knowledge, further experiments were conducted, which shows that matter was made of other particles that are smaller than atoms. Example, electrons, protons, and with their discovery, with their experiments. And we are going to look at some scientists that did some contribution to this work. So J.J. Thomson and Robert Millikan did some great contribution to the fact that atoms can be destroyed. That atoms are made up of other smaller particles. They are not indestructible as proposed by Dalton. So let's look at Thomson's experiment. Thomson's experiment. Thomson designed an experiment to study the properties of cathode ray. But what are cathode rays? These are rays produced when an electrical voltage is applied across electrodes of an evacuated glass tube. So this is the evacuated glass tube. It means you don't have any gas inside. Evacuated glass tube means it's a vacuum. There's nothing inside the tube. So this is the electrode, this is the cathode, and this is the anode. But this tube is a vacuum. There is no air inside, there's no particle inside, there's no mass inside, there's no substance inside. So Thomson investigated the effect on a cathode ray by placing an electric field around the tube. The charged matter is attracted to an electric field, but light is not. I want you to take note. Charged matter is attracted to an electric field, but light, our normal day-to-day light, is not deflected, it's not affected by an electric field. So inside this tube there was a glow, there was a light. So they didn't know whether it was just normal light or it was a particle. But the only way they could know whether it was a particle if it is deflected by an electric field. It shows that it's a charged matter. So that is what he did with his study. And why was it called cathode ray? Because it was always from the cathode to the anode. That's where it was coming from. It was coming from the cathode and going to the anode, attracted to the anode. And when he had an electric field, you see, it was deflected, which shows that it's not light. It's a particle of matter. So the amount of deflection was related to two factors, the charge and the mass of the particle. These particles have negative charge. Why was it sure that it had negative charge? Because the beam were always deflected towards the positive plate. When the electric field was put there, it was deflected towards the positive plate. And the charge to mass ratio that Thomson obtained from his experiment was minus 1.76 times 10 to the 8 coulombs per gram. So from his experiment, that was the charge to mass ratio that he got from his calculation. So, Thomson's conclusion from his experiment: if the particle has the same amount of charge as hydrogen ion, then it must have a mass almost 2,000 times smaller than hydrogen atoms. So the charge to mass ratio for hydrogen was observed to be this. So with this, Thomson believed that these particles were therefore the ultimate building block of matter. And from that, he gave it the name electrons. So he gave it electrons. So Thomson was credited with the discovery of electrons. So he came up with the charge to mass ratio of an electron. From there, Mulliken came up with his own investigation to find out the charge of an electron. And he conducted his experiment, which is known as the Millikan oil drop experiment. He used finely sprayed oil droplets to determine the charge on the electron. And what he found was that the measured charge on any oil drop was a whole number multiple of minus 1.6 times 10 to the minus 90. And he said that this number is the fundamental charge of a single electron. So you can see how the experiment was conducted. He used this container. The atomizer atomized the oil and it was produced as a spray inside this tube. And inside this tube, you have this plate, positively charged plate, but there's a hole there. And the oil was dropping, you see the oil dropping. And by the time it was dropping through a chamber that air that was it has been ionized. So these oil droplets were picking up charges. And investigating the charges that these oil droplets were picking, he noticed that it was a multiple of minus 1.6 times 10 to the minus 19. That is how he came up with the fact that the charge on an electron is minus 1.6 times 10 to the minus 19. So with that, Dalton's atomic theory was being modified. So since atoms were found to contain negatively charged particles, electrons, it shows that Dalton's atom is destructible and atoms have particles. But new questions came up. Since atoms are neutral, are there some positive charge particles in the atom that neutralizes the negative charge? Those were questions. If a positive charge exists, how do they interact with the electrons? And where are these negative electrons and positive charge located within the atoms? These were questions that came up, and further investigations were required and which were done. So Thomson's idea of an electron with those questions, of an atom with those questions around, he came up with the fact that based on these new questions, Thomson proposed a new atomic model to replace that of the atom. So look at this model. This is his model. He said we can relate it as Americans to blueberry muffin. That's how we can relate it. But in English, they call it the plum pudding model. So the structure of the atom contains many negatively charged particles known as electrons. This is his idea. And these electrons are held in atom by positively charged sphere. That was his idea. And with this idea, the picture he had in his mind was this. You see, as I said, for us Americans, we can look at it as a blueberry muffin. But this was his idea. This was his thought. But in chemistry or in science, you need to conduct experiment to confirm it. So in the course of trying to confirm the experiment, he needed something to penetrate the atom. So with that, we'll talk about radioactivity before we go to the experiment. So by late 1800s, Henry Becquerel and Marie Curie had discovered that certain elements would constantly emit small energetic particles or rays. It means they just break down on their own without you activating it. That is how those elements behave. We call them radioactive elements. And these particles were energetic. So energetic particles could penetrate matter. And so these were the particles which were radiated that could penetrate matter. So when this was already discovered, they used some of these particles to penetrate an atom to study an atom, to see how the electrons and the protons or the other particles are arranged in the atom. So the three different kinds of emissions that were discovered were alpha particles with a mass 4 times that of hydrogen atom, and it has a positive charge. Beta particles with a mass 1/2000 mass of an hydrogen atom and has a negative charge. Then you have the gamma ray. This is not a particle, it's just a ray. So with this idea, with this knowledge, Thomson had to use alpha particle to investigate the structure of an atom. So let's look at how Thomson did it. Thomson himself did not carry out the experiment. He had a student called Rutherford, Ernest Rutherford. It's Ernest Rutherford that he sent in the lab to conduct this experiment. So Rutherford was Thomson's student and supported the Thomson's famous plum pudding model of the atom. So Rutherford designed an experiment to confirm the plum pudding model. He was just going there just to confirm what his boss has already come up with. So what did Rutherford do? He used alpha particles to probe the structure of an atom by directing the particles towards a thin gold-foil. And when they were conducting this experiment, they knew that all the alpha particles was going to go through, because they believed that the positive charge in the atom was so dispersed that it could not stop the alpha particles from passing through. So this is the experiment. You see the example. This is the source of the alpha particle. This is a detector, and this is a thin gold foil that was placed, and they were firing the alpha particles through it, expecting it, all of it, to go through. That's what they were expecting. But surprisingly, you see, this was deflected. Some even came back. You see, this came back. So these are all alpha particles. They were expecting all to go through, but you see, some got deflected, then some even came back. That's what they were expecting. If an atom was like a plum pudding, all alpha particles should go through straight. But almost all alpha particles went through straight. But some alpha particles go through but are deflected due to positive repulsion from the nucleus. So it means this is not how the protons and the electrons are arranged in an atom. So you see, a few of the particles do not go through. So from Rutherford's result, over 98 of alpha particles went straight through, which is what? But about 2% of alpha particles went through but got deflected by large angles. And about 0.015% of the alpha particles bounced off the gold foil. So in conclusion, an atom is mostly empty space, because almost all of the particles went straight through. An atom contains a dense particle that was small in volume compared to the atom, but large in mass, because of the few particles that bounced back. And this dense particle was positively charged. Why? Because the light deflection of some of the alpha particles are positive. So they made this few that were in the center that were positively charged. Of course, positive will repel one another. So now a new model of an atom was being proposed. Rutherford interpretation on the nuclei model. So the atom contains tiny dense center called the nucleus. And the nucleus has essentially the entire mass of the atom. The electrons weigh so little, they give practically no mass to the atom. And the nucleus is positively charged. The amount of positive charge balances the negative charge. Of the electrons. And the electrons are dispersed in the empty space of the atoms surrounding the nucleus. So, the atomic structure. So, this is how the other particles of an atom were being discovered. So, let's look at the atomic structure. So, the structure of an atom. So, Rutherford proposed that the nucleus had particles that had the same amount of charge as an electron, but opposite in size. And based on measurement, the nuclear charge of the element, based on measurement of the nuclear charge of the elements. And this particle was called a proton. So you can see its charge, but look at its mass. And since protons and electrons have the same amount of charge, an atom, for the atom to be neutral, there must be equal number of protons and electrons. So that is how an atom and the subatomic particles of the atom were discovered. Rutherford experiment was highly successful, but was incomplete. For instance, hydrogen atom contains 1 proton and helium atom contains 2. Yet helium to hydrogen mass ratio is 4:1, not 2:1. So what accounts for the additional mass? That was the question. So with that, further experiment was conducted by James Chadwick. And it shows that there is an additional particle in the nucleus that is neutral. That particle is neutral. But the mass of this neutral particle were approximately equal to the mass of the protons. And this particle, they gave it the name neutrons. So in summary, an atom has 3 subatomic particles: proton, electrons, and neutrons. Proton and neutrons have almost the same mass, and their mass is about 2,000 times larger than that of an electron. But the proton and nucleus are located in the proton and neutron are located in the nucleus. Meanwhile, the electron is located in the empty space. So the charge on the proton is +1. The charge in the electron is -1, which are equal in number and makes an atom neutral. These are some of the symbols which are used. For proton, we can use P, we can use P+, we can use H+. For electron, we can use E or E-. And for neutron, we can use N or N0. On that, we will conclude this section of chapter 2. Thank you.